Je le connais. Attends, juste passe sous sa caméra, il est là-haut.
President Mayor presentation. And also, I want to thank Mr. Alexander for all his efforts with me. Then, my name is Mohamed AMAR, PhD student, Laboratory of High Energy and Astrophysics, Oakington Observatory of Marrakesh. Today, I will be presenting of detection and the effects of black hole variation in the RR library of stars. This research is essential in understanding stellar oscillation and their implication in the astrophysics. Next plan. Firstly, I will see the introduction and general information of the variable stars and the Oakington Observatory and results and conclusion. Introduction. In the heart of the cosmos, stars dance on the earthly reasons. Precision like celestial headspace joined as we delve into my series of stellar precision and their pivotal role in the universe cycles. And what is stars? Stars is the massive luminous sphere of plasma held together by gravity in the hydrostatic equilibrium equation is social that the inward gravitational phase is balanced by the outward pressure of the gases. Solar formation. Stars are born, evolve, and eventually die. The life cycle of stars depends on its mass. This image outlines the stage of stellar evolution from the formation of stars to their end stages. Stellar formation. Solar oscillation are period expansion and contraction in the outer layers of stars, and this oscillation provide valuable insights into the internal structure and properties of the stars. Can you see that for the type of solar oscillation? There are too many types of solar oscillation, the radial mode and the no-radial modes. The radial modes envelop stars expanding and contraction symmetrically. The displacement is a function of ratios and time described by the amplitude and frequency. And no-radial modes occur when different parts of the star's surface move in and out of the phase, and the displacement psi depends on symmetrical coordinates and times. And in part 2, I will say general information of the variable stars. The variable stars is whole brightness change over time. This variability can provide important information about stars' properties and behavior. This is the three light curve in the variable stars. Type of variable stars. The variable stars are classified into two main categories: intrinsic and extrinsic. Intrinsic, where the variability is due to physical change with stars, and extrinsic, where the variability is external factors such as eclipse in Venus and rotation variable. The type of the RRI stars, the class of the RRI stars is polarization regions and solar is population 2 and period under 0,2 and 1,1 days. And spectral type is E to F. And temperature is 64 Kelvin and 74 Kelvin. This is the image of the variable stars. Precision mode of variable stars is the RR Lyrae, is a radial mode. Precision mode. Stars can presage in different mode. Radial precision mode described by a number n, and non-radial precision mode described by n and l and m. This is classification of the variable stars RR Lyrae. The RR stars are classified based on their light curves. And dominant pulsation mode, the RR AB fundamental radial pulsation mode and RR safe first over 10 pulsation mode and RRD mixed pulsation mode involving both the fundamental and first harmonic. This is pulsation mechanism. Pulsation mechanism are block of transformation of the pulsation mechanism, the energy to thermal energy and causing change in temperature and density and opacity and pressure with stars. Delays on the formation and of the propagation of the shock wave. The Blasco effect, named after Nikolavich Blasco, is a moderation of the amplitude and phase of light curves. Some RR Lyrae and RR Scuti stars. This phase designated by Psi. Shock waves. The position in the RR Lyrae stars are interpreted by the existence of shock waves traversing their atmosphere with H position. Shock waves in the RR Lyrae stars produce distinct spectrophotometric signature which can be used to study in the internal dynamic of test stars. The Foucault RR41 model describes the evolution of 5 shock waves, with his model described 2 shock waves per pulsation cycle. And this part I share with you the Oakhamden Observatory. The Oakhamden Observatory is the astronomical observatory located in the commune of the Oakhamden in the Atlas Mountains of the Morocco, where the Morocco Oakhamden Sky Service is conducted to observe small solar system bodies. This is couple where I study in the solar spectroscope. The materials, if the instruments have a telescope made size, the perceived size inch, and camera CCD, and HS spectrograph, and third are calibration units and gain units. And this is the example of the spectroscope. I share with you some results. This result is the collaboration between the Oakhamden Observatory and Observatoire de Haute-Provence in France. Professor allocation on two telescope 2015 and 2016. The measures combined of 2015 and 2016. 69 spectra of the RLI recorded as the Oakhamden Observatory. The first fact, diversity of the helium emission in precision variable stars and RLI type. This is in comparison in Chile and 29. And second effects, diversity of the helium emission in the RLI. And third fact, viscosity of second helium emission in the RLI type. And this is the comparison with telescope in the Oakhamden and telescope in Chile. This is some results. And this is the calculation of the radial viscosity and shock wave viscosity in the RLI. And this is the result with the antiphase graphite spectral Teca spectrum. This is the OGCL with the created by this level. This is one D curves and the supplies. And this is the overlapping spectra, the one dimension. And this is superposition of the line profile of the helium. And this is the one dimension and two dimension spectra figure. This is the detection the helium H alpha in the RLI in 2015. And this is the comparison with the different nights. And conclusion. Sum up of the Oakhamden Observatory has played crucial role in the study of the variable stars through its research effort and precise observation. It has significantly contributed to our understanding of the solar phenomena and expanded our knowledge of the universe. Depending have not only enriched our understanding of the variable star, but have also paved the way for future research in the existing field of the astronomy. And this is the future conference this year. This is the RLI and SAFRAN meeting 24 is November 18 to 30 of November. And this is the same spectroscopy solar in the Oakhamden Observatory. And thank you for your listening.
Test. Perfect. Okay, so thank you very much, Mohamed.
Thank you.
Is there any questions?
Yeah.
Okay, so you don't see the room, but no one seems to have any questions. In any case, if you have one or more questions, you can ask me, and I will tell you the coordinates of Mohamed. Okay, if that suits you, Mohamed. It seems to. Okay, so perfect. Thank you very much, Mohamed. And so now we. Okay, so now we have the pleasure to welcome Mayssa DALDOUL for a new presentation. So, please.
And thank you for your
Thank you very much.
Hello everybody. Today I'm here to present my presentation about impact craters. First of all, my name is Mayssa DALDOUL and I'm from Tunisia. I'm a student in the second year of master in the Faculty of Science in Tunisia. So here I will tell you about all body solar system have been impacted, and so impact craters is a phenomenon very common in all the solar system. My future thesis will be focused on understanding and improving our knowledge to understand how it caused and how it be formed, etc. So impact craters, in general, it's produced by intense shock waves that are generated at the point of the impact, and the sources of impact craters are asteroids and comets. So asteroids and comets, as you can see here, are very small rocky bodies, and as you can see here in the belt, in the green belt, there is the asteroid in the belt between Jupiter and Mars. In red, here we can found, if you see the little point in red, these are the near-Earth asteroids that cross the Earth orbit. So the stage of crater formation are three. Here, the first stage is contact and compression. This stage begins at the impact that the impactor makes contact with the surface floor, and this initial contact generates immense pressure compressing the target material. The second stage is excavation, and as the impactor penetrates in the target, it excavates material, creating a cavity and ejection materials outward. The final stage is the modification stage, and it begins when the transient crater has grown to its maximum size and it lasts a few hours and depends on the size of the transient crater. So the types of craters are we have a large type of crater, so it also depends on the size, the terrain, angle, and so there are various types of craters. For the smallest size, the transient crater undergoes later modification. The crater takes on a ball shape. And it's called sample crater, like you can see here, the example for crater Zomba on Mars with 3 kilometers in diameter. The larger transient crater size when the material of the center of the depression rebounds after the impact. It depends forms, and here, as you can see, the peak central, the collapse. For example, we have crater Kuropiok on balloon with 93 kilometers in diameter. And for the largest crater size, here, when the material raises in the center from one or more rings, and it forms a multi-layer of rings. As you can see, here the largest crater type is the crater Lowell on Mars, for example, with 202 kilometers in diameter. The examples of different other type of impact crater, here we can have simple impact crater with ball on Mars with a 3 meter in diameter. Here we can see the rays, etc., and the rays of ejecta. We have the complex crater with central peak, like Tycho on the moon, with 86 kilometers in diameter. And then we have ringed basin or ringed crater, or crater with rings. Oriental basin on the moon with 950 kilometers in diameter. So here we can have the lobate ejecta crater, the other type of crater. The lobate ejecta crater, it depends on the target material, which contain ice and volatile. This is why we have the lobate forms of ejecta. We have also linked Martian oblique crater. This is caused by an angle because when the asteroid took in contact with the target material with an angle under of 50 degrees. We have also double crater. This double crater due to linked to the fall of double asteroid. And we have ghost crater. The ghost crater is covered by the lava. And here, as you can see, it's about 100 kilometers in diameter. So on Earth, we have only 200 impact craters. And why? It's just simple because plate tectonics erase this structure. And how can we study the formation of impact crater, knowing that the majority of them were formed billions of years ago and lack of rock samples? So the disruption of terrestrial impact crater, as you can see here in the north and in the north of America and in the Europe, but in South America and in Africa we have just a few impact craters. More than their half are located in the Europe and the North America. So the largest crater, as you can see here, the largest crater are over 10 million years old. In the picture, as we can see here, it's between 9 meters. The craters between 9 meters and 1 kilometer are older than 10 million years. And the concentration of impact craters, they are bigger than 10 kilometers, are older than 10 million years. So in this picture, we can see the cross-section showing peak shock pressure, isobar, at depth of 2,000 kilometers. The pressure reached 10 gigapascal, and we can found this. We can see it is an impact crater. When we will found these types of rock, here this is the shock quartz. This is the second pit present the shattergans, and the third picture present breccia impact. Okay, this is the type of impact craters on Earth. Here we can have in Libya, in Australia, in Brazil, with a variety of diameter and variety of ages. But in the world, we have the biggest and the largest, oldest terrestrial impact structure is Fred 4, and is located on the South Africa with 2 billion years old, and its size vary between 200 and 300 kilometers in diameter. As you can see here in the picture, we cannot see exactly where it is, and here, this is the structure very it is identified, and it's clear. Meteor crater is the young crater on Earth, and it is well-preserved, well-known impact crater with 1 kilometer in diameter, and its example for sample crater, it has a ball form, and it is with an age 50 million years. So knowing that we don't have this type of crater on Earth, complex crater on Earth, how can we understand the formation of them? As you can see, we don't have a large crater on Earth, and we cannot study the complex crater on Earth. So we have the moon example here, as you can see. Complex crater and very large impact craters. The fresh impact craters have rays, and this is the picture of secondary craters that can be existed on the rays due to the ejection material from the impact crater. So we look for crater on Mars that have these characteristics, and to more understand their formation. Okay, so here blue rays indicate the secondary crater. As you can see here, they are the legend between blue and green, the smallest crater that can indicate the existence of a youngest crater. So as you can see on the curve, they are older than 10 million years old. So we use with Anthony Lagan use the database which contain 90 million crater impact to do this exercise and find the craters on the whole surface of Mars to understand, to take the impact craters. They are very young. They are very youngest. As you can see here, the description of the secondaries, the rays, it tells us they exist, the youngest crater. So, for example, here, during my stage here, I study Kotka crater in Mars, located in Elysium Planitia, with 39 kilometers in diameter, and it have a multi-layer ejecta blanket. So here I will tell you how I do the map of impact crater. This is the picture of the crater. This is, as you can see in the middle of the crater, the peak, the central peak, and then the pitted material in front of the crater and wall block material. Then this is the crest stream. It's well defined, and these eroded formations are present the most in the recent crater. We can see this formation of the recent crater because they are very preserved. This is the map of Kotka that I have mapped it. And this is the other crater with the same method I have made them. So we have Kamala, we have Mojab, we have Zunil, and Gaza. For my next perspective, I will do the statistic analysis. I will do calculating the perspective for the altitude, the surface, etc. I will generate a DTM with the CTX pictures, CTX pictures with very high resolution. And then I will do the comparison with the terrestrial crater. And thank you for your attention. Any question?
So, is there any questions? If we are so clear, maybe?
Hello, thank you for the amazing talk. The most of the craters you showed were round craters, but wouldn't most meteors come from the side? Like statistically, if you have like a ball, wouldn't most of the meteors, if they were to strike the moon, wouldn't they come from an angle? And wouldn't you get more angled craters then?
Yes, we can have craters with an angle, and they can form no circular, just circular crater. We can have also more forms, but here in my study, I just study for the youngest crater, and it will be just informed circular, not exactly circular crater. It can be sigmoid and etc., but their form in general are circular depression.
Okay. So do you have any other questions, maybe?
Okay, so I've read about the type of research when you try to simulate the actual impact. How do you do it nowadays? Because I know that in the past there was this experiment. Someone at home dropped like a rock or something into just a powder. Is there an easy way, or not necessarily easy, but more representative way to simulate this?
It's okay if I understand your question. You talk about how can we know that this is a crater impact, not is a simple circle. This is it. So we can know that this is an impact crater when we can found the rocks around in voilà. When we can found the rocks in the target rocks on the target target floor, we will found these rocks, and this is how can we see this is an impact crater with this type of rocks.
Do you have some type of spectrography to do that on other planets, or is it
Somewhat?
Spectrography or something to identify these formations?
Yes, on Earth we found these rocks, and we have on the Moon too these types of rocks. That's why we can see it's a crater, and then we do this experience on the Mars with the robo, etc. That comes back with these rocks and the existence of a crater.
Do you delve anything more into the dynamics of the formation, or do you just look at the remnants mostly?
I don't understand what exactly.
Do you look at the formation of the craters, like how the matter is distributed during the shock, or do you mostly look at what happens afterwards? Or what?
We see what happens after the shock.
Any other questions? Okay, so perfect. Thank you very much. So now, just before we have a little break with snacks and drinks, just a little reminder, because you know, this edition was a real pleasure to organize. But next year we'll need more help with volunteers, etc., in the organization of a new Congress, ICAY 25. So if any one of you wanna just invest yourself in the organization or just the D-Day of the Congress, do not hesitate to just come to us, maybe.
Yes, and furthermore, the next edition will be hosted in France too, but we would like to continue the ideal we are pursuing of like gathering together in the same structure all the astronomical societies in the world. And so if in your country or anything there is other astronomical societies that could be like able to send some delegations to, of course you can just like link us with them, and also in a future edition, like maybe in 26, 27, we would like to do the ICAY in other countries, maybe like in Stockholm, in Sweden, or anything else. And so for this type of things, we will need, of course, also a team in the hosting countries. And so if you think that your country or associations could, I would say, fit the size or the importance of the ICAY and just like could host us in a few years, then yes, really feel free to contact us. You have all the emails available on the website or anything else, and we can connect and we can try to do such type of things, I think.
Yeah.
So that's all.
And even on the simplest level, if you're just a single person that want to invest themselves in the ICAY organization, as in the same way I as organizing in distance the edition, programmation, communication, etc. We have a wide range of things to do. Everyone should found what they want to invest in ICAY. So just if you have ideas, if you are interested in a particular sector of organization, or if you are just volunteer to help It will be a pleasure, even if you can't come to ICAY 25 or an edition, it's not a problem. We're of course, really happy to see you all. And of course, to the next edition, you are all, of course, invited. So we stay at your disposal if you need anything, any information on that. So now there will be a break of like 30 minutes, half an hour, so you can relax, drink, discuss a little bit, and then there will be 2 other presentations before the unfortunate end of this Congress.
Actually, theoretically, we were supposed to have a presentation from the CNES. However, they have cancelled it recently, so we have no choice but to. We couldn't find someone else to replace them. So the next we have log, so an half an hour break, and then there will be a Sanctuary on the Moon, which is an initiative supported by France and NASA, and a talk by SAFRAN, RIOSC, which is the enterprise that is, realizing the mirrors for the EELT, the European Extremely Large Telescope. So this will be, I think, extremely interesting.
Thank you, everyone.
On met un petit Spoutnik métronome, quoi. À rien. Ouais, ouais. C'était d'abord une reproduction de Spoutnik, en fait.
Okay, so thank you everyone. So we have the honor to welcome Benoît Février, who will be presenting the Sanctuary on the Moon project. So thank you very much for coming. And there will also Jean-Philippe Uzan, who have been already presented, but he is a cosmologist and physicist and theoretical physicist. So thank you, both of you, and the floor is yours.
Thank you very much. I'm going to begin this keynote presentation by telling you a little story. Of course, you guys know everything what happened in 1957 with the first launch of the first man-made object to space, which was Sputnik, sent by USSR. I believe it was in October of that year. And I wonder if you guys know how long Sputnik stayed up in orbit. I believe it's up to only a few months. Funny enough, France decided to launch another satellite in 1965 from its Algerian base in Sahara, which was called Asterix. Asterix is a very famous character in France and all over Europe, I believe. He is supposed to be iconic of the French spirit, the French, I wouldn't say the French chic, but the French resistance. So, and the satellite was named Asterix. And because Asterix was sent in a highly elliptical orbit, the satellite is still up there and is going to burn up in the atmosphere in 5,000 years. 5,000 years is a very long time. Actually, Christianism was born 2,000 years ago. The pyramids of Egypt were raised 5,000 years ago. The paintings in the Lascaux caves are 70,000 years old, and the Grotte Chauvet in southern France is 34,000 years old. A few years ago, I assembled a team of researchers in France, in Europe, in Canada, and the US. And with the inspiration of the golden record that was sent in 1977 aboard the Voyager's space probes, we decided to make some kind of golden record V2.0 that would not reinvent the wheel, but that would tell something else. The golden record was sent for extraterrestrial intelligence, and it is supposed to last billions and billions and billions of years. Why is that? It's because, as you all know, space is full of nothing. And we came up with a project called Sanctuary, because Sanctuary is a place where you put something precious. And it took a few years to develop, at least the first version of the project. And back in September 2020, I approached NASA with different members of the Sanctuary team, an American guy called Michael Benson, and we showed all the content that we engraved on some of the disk and what is Sanctuary supposed to be in the near future. NASA loved the project so much that it granted us 1.4 kilograms that will be placed on the US space probe for the Artemis program. The Artemis program is twofold. One is a manned space program, and the other one will be automatic space probe sent either on the equatorial region of the moon or the southern pole. And we have 24 disks engraved at the Commissary Atomic Energy in France, in Grenoble, on which we can put up to 7 billion pixels per disk. Sanctuary is there's such a lot there's a lot to say about it. When I started the project, I wanted to stick to the inspiration that Carl Sagan, the famous astrophysicist, had, was to bring different researchers and show what our knowledge could be to extraterrestrial. We have an heterogeneous team of specialists from different disciplines. Jean-Philippe here is an astrophysicist, we have paleontologists, we have particle physicists, we have graphic designers. There's a lot of the diversity of the disk that I'm going to show you afterwards. The content is not yet finalized and is yet to be written. It's a space epic because sending stuff to space is nothing common. And it's a human adventure because I am trying with the team to bring all together geneticists, researchers, scientists, and artists. It's also a node to knowledge because knowledge is at the heart of this adventure, and it's raison d'être. Starting with Sanctuary, I assembled different partners with INRIA, which stands for Institut National de Recherche d'Informatique Appliquée in Saclay, Commissariat Énergie Atomique, Commissary for Atomic Energy in Saclay as well, the French National Space Center. We got the genomes at the Michael Smith Science Genome Center in Vancouver, and once we gathered all these partners, we approached UNESCO and NASA finally back in 2020, and the agreement was awarded in 2023. So where we came from? As I said, Sanctuary takes its inspiration in past projects. On the bottom hand left corner, you can see the Pioneer plaque that had been designed by Carl Sagan in 1972 and that boarded the Pioneer probes on its voyage to the outer skirts of the solar system. 5 years after came the Voyager space probes, on which the team, Sagan, Frank Drake, and John Lomberg, Andrew Young, and some other people managed to encode images within the grooves of the golden record. And the disk was beautiful. It had like 55 different languages, a hello in 55 different languages. It had Mozart, Bach, Beethoven, Stravinsky, Blind Willie Johnson, Chuck Berry, and so on. So where are we going? With Sanctuary, we are not, as I said, trying to invent the wheel. We want to send a message, a different message that would have content that has never been seen before. When I started Sanctuary, what I knew from the very start that it would be pointless to copy-paste content from the internet onto some analog content, on some analog support. So we wanted to have original content developed especially for sanctuary. And why is that? It's because it's going to be much more relevant to have it exploited afterwards on Earth. What you have here is one of the biggest displays in Europe. It's basically a gigantic iPad where you can pinch to zoom with your fingers, and this is a tool at INRIA that we used to display all the content of Sanctuary, from workshop to other workshops. So the first workshops were organized in 2017, and then there were other workshops along the year in up to 2018. That was for the Sanctuary V1. And from workshop to workshop, the content had been iterated, and then we came up with the content that we're going to showcase to you in a few minutes. As I said, I assembled a team of different researchers, and you can see them all here. They range from engineers, designers, computer scientists, astrophysicists, medical scientists, cosmologists, particle physicists, geneticists, and so on. And Sanctuary, as I said, is 24 disks, 10 centimeters in diameter, are going to be brought to the moon. So 5 of them is going. Sanctuary basically is a triptych. I love summing up things, you know, some kind of elevator pitch. What if we were to sum up Sanctuary? Sanctuary would be what we are, with 2 full human genomes selected in a double-blind process at Canada's Michael Smith Genome Science Center in Vancouver. What we know, and that was the hardest part, a selection of knowledge regarding different themes: time, water, matter, life, and space. And then we have some of the disk, what we make, and this is the last part of the triptych. All the disks are engraved at the Commissariat Énergie Atomique, Commissary for Atomic Energy in Grenoble. And as I said, we have 3.4 to 7 billion pixels per pixels. And if we want to have top-notch precisions within the grooves of the disks, not the grooves, but on the surface of the pixels, it needs to be engraved properly and very cleanly. And as a matter of fact, we use one of the highest ranked clean room in the world. So basically, if you were to send 1 hour under the Eiffel Tower, you would breathe the same amount of fine particles than spending 5 years inside a clean room. I wouldn't recommend spending 5 years inside a clean room, but when you get the point, everything is super clean. Basically, you don't have to pass the vacuum cleaner anytime because there's no dust, there's nothing. I'm going to show you some of the excerpts. This is a genome disk. This is the first disk. So the female disk, the female disks are spread on 2 disks, and this is one of the 2 disks. Then we have one male that is same. It's like two disks for one male. And then I'll showcase to you the science disk afterwards. I believe that I'm going to start with the science disk with Jean-Philippe. And Jean-Philippe, if you can come on stage. So I'm going to start all the disks we have. So I am taking the example of the space disk, and here is live disks. All the disks have the same features, or approximately the same features at the very same location. Here at the very center, if you want to convey information in the far future, you need to start with the basic. And what is the basic? It's the standard unit of system.
Vous connaissez ça. You have seen that before, I guess. Yesterday? No, yesterday you were, this is what we saw yesterday at the Bureau International des Poids et Mesures. So these are the basic units.
I believe you need to speak directly in your microphone, or otherwise it is.
I'm too far? Is it okay? So the question is that if imagine you want to, as you explained, Benoit, you were talking about aliens, but even if you think about humans in, let's say, 10,000 years, they won't speak French, they won't speak any language we know, so there is no way they can understand us. So if you want to talk to the future, you have to imagine that you are talking to aliens. Okay, this is what has been done when people were discovered, you know, this, they want to understand hieroglyphs, they needed something to translate. So Champollion, he had to understand the language from aliens. So what is the basic things to communicate to any living species who is intelligent? This is mathematics and physics. Because we think this is something universal. We all have 0 and 1. We all have the same kind of mathematical operations. We don't write them in the same way. So you cannot assume that the cross is a plus for any languages, that the 0 is represented by this, the 0 and the 1 by the 1, the way you are writing them, but the concept should exist. And also, we know that whatever is in the universe, it will be made of the same atoms. Hydrogen, helium, carbon, they would be the same all over the universe. If it were not the case, then the universe wouldn't be understandable by us astrophysicists. That we know. So now if I start to understand, okay, hydrogen. Hydrogen is the most common atom in the universe. It has, for instance, a 21 centimeter line that any astronomer who has looked at the sky will be able to detect. So if we are able to say, okay, this is what we call the 21 centimeter line of hydrogen, and to explain that, and say, okay, the wavelength of this radiation is 21 centimeters for us. Maybe they will measure this is 500 and I don't know what, a unit I don't know. They can translate. Okay? They can translate. And if we have the basic element from mathematics, fundamental physics, we will have a kind of a dictionary. And then we will be able to define second, ampere, kilogram, and all these things. And further on in all the data that we will be able to use these units because they will have been defined. Okay? So the question, the fact that we don't want, as Benoit said, to reinvent the wheel from the golden record, but we have to put some basic elements coming from fundamental physics, chemistry, and mathematics so that the content of the disk are understandable. So here we have the unit systems. So here you see there is something about the speed of light.
But we need to look at the SI system as some kind of alphabet that we are trying to define from the very scratch.
Yes.
But if it's not the only thing that needs to be defined from the very scratch.
No.
We are trying to define as well languages. And how do we convey the meaning in languages? By displaying the content of the Universal Declaration of Human Rights in different languages. So here you have them in Georgian, Maldivian, Hindi, and Armenian.
Yes.
And say for a different disk, say here on the live disk, on the outskirts of the disk, same here, you would have Arabic, Greek, Russian, and Chinese. And so on, different language and on different disks. And here, at the very center, same. We define another unit. Here we define a unit of temperature, which is the Kelvin. And with all these units combined, you can say a lot about the universe and what we know about it, what we know about life, size of animals, the age of the universe, where we've been to, what we've discovered, and a lot. Mm-hmm. And of course, some of the graphs and some of the information displayed on the disk can be a little mysterious, but we like this kind of mystery. We like the fact that our descendants in the long-term futures or other beings would be able to fiddle with the disk and wonder what did it mean by that. For instance, here, and this is something that I love.
What is this?
We show I'm sure you guys think that, well, you know, it looks like a map of the world, doesn't it? In fact, we compiled every flight taken in the year 2020 to show that we lived in a connected world. And because the disks are semi-transparent, a map of the world would be stacked to another map of the world. If you were to stack all the disks together, and here we have all the roads or highways in the world. Here you have France. And we have different, okay, here's anatomy, right? And here we have the nervous system. And at the very same location on the space disk is a naked woman. So if you were to stick that woman on top of this, you would see the nervous system, the blood system, the organs, and so on. And because, okay, I'm going to show you this because it's something that I love as well. It's here. You can see obviously the sun, but what has been shown here is we compiled all space missions ever made by humankind. So here you have the sun, Mercury, Venus, the Earth, and the Moon. Mars, we have Ceres in between Mars and Jupiter, and then Saturn, you name it. And here are all the different occurrences plus flybys of all space missions since the first object that reached the moon in 1959, that was Luna 2, I believe. And how do you date event? We didn't want to get the Julian, Gregorian, Islamic, or Jewish calendar. We used a universal calendar on which we display the date with the location of the planets at a certain time on a given day.
Yeah, so if you give the position of all the planets in our system, basically you will know what is the date. Okay, and of course you have some recurrency, but it's thousands of hundreds of thousands of years. So the point is that no calendar makes any sense unless you have defined. I mean, you have to say what is a year, what is a day, when does it start. It's too many things to define. When you look at the solar system, if I give you the position, you know basic astronomy, which would be the case of any intelligent species, then they can go back. I mean, this is like the software you are using. I mean, you want to see what is the sky next week to prepare your observation, or in 20 days or a year from now, you can do that. So the question is that this can be computed very easily if you know the motion of the planets. So it's such a thing is a datation. So this is the position of all the planets in the heliocentric system, and from this, you have a pure datation of any event. So we can put this small symbol of the position of the planet if you want close to a picture, too close to a text, and it will tell you when this text, so this will be a way to date all the events we have on the disk. So astronomy for this is the best timekeeper we can think. It's not the most precise, but this is the one that you have to use our long time scale. We are not interested in precision at the level of a year or so, but so it's enough for us to, yes, here.
So I just put some kind of random note that was the 21st of March in 1959, and it gives you the exact location of the planets at a given day. I'm going to show you some last features because, and this is something that I love as well. There is, let's face it, I wouldn't say hardcore science. I didn't show you the matter disk on which there is particle physics, and to tell you the truth, particle physics can be a little too harsh for me. But what you can see here is, of course, a fetus gently sleeping in the womb of his mom. And you can see here you have squares. And in each square, there's the exact number of people speaking a given language. So here in this square, you have 82 million pixels. And what is here is a lullaby.
In Javanese.
In Javanese.
So because we wanted to give an insight of what is universal, so we talked about the laws of nature, but we also wanted to say we are humans, and humans is not just one human. It's a diversity of humans speaking different languages, looking differently, having different cultures, and that was our problem actually. How do you show diversity? And the first thing we wanted to show is that there are about 3,700 languages spoken on the earth today. They are not all represented because some of them, they are spoken by, let's say, 10 to 20 people. But most of the languages, I think we have about 1,000 of them, have been compiled this way. So you see the languages which are spoken by huge community and the one which are spoken with small communities. And there is always the name of the language and of course, some kind of text in this language. So of course, we cannot explain all the Japanese, the Chinese, and everything, but we want to show that humans have been using different languages to discuss together and to communicate. And as Benoît was saying, this is also in mirror with what we had, the translation from the Universal Declaration of Human Rights, because this will be in 20 languages, 20.
Yeah, there would be 20 languages, and it would be like the second most translated text after the Bible, and we didn't want to take some religious text to display the content. So the Universal Declaration of Human Rights is a strong statement as well.
Yes.
So there are the 5 official UN languages that are Chinese, Russian, French, Spanish, and English. Plus we used rare languages or languages for which the typography is really beautiful.
Yes, like the language of Inuits, the Eskimos. It's a very beautiful language, and we're using this also. And so you see, the idea was not to be, we cannot compile everything because this will be like a full encyclopedia. It's impossible to do. As Benoît said, it would not be interested to put, I mean, at the beginning we said, it's enough to take all Wikipedia and to put Wikipedia on these things because then there will be a lot of knowledge and you can go through. It's not interested. It has to be curated. It has to be something that tells you that it looks like a piece of art because we want also to show that humans have been designing art. They have been playing. You showed the chess game. So we wanted to show what we know from the world, how we figure out how we localize humanity in space, in time, in the living. So this is why these 3Ds, they are kind of localization of us as human in all what we know that exist. And then we wanted to show things that humans are doing. And also that you cannot be complete. You have to make choices. And so, for instance, we wanted to show that humans are playing. Playing is a very important thing. So we have chess game, we have the Go.
Exactly, with the most played, with the most played game in the most famous game in the world, and we included, of course, the rules, the chess rules.
So you have the rules, and then you have some famous chess games that have been played on the earth. The same with Go. You have Awele. I don't know whether you know this African game with seeds, and so on and so on. And also we try to explain how much we understand about the world. And I think there is. Do you have a Game of Life somewhere? But
yes,
it's okay if you don't have it.
No, we do have it. But I can't remember the location of it.
So Game of Life is a cellular automata that was designed by Conway, a mathematician, and basically you have squares which are black and well, it allows you to play a little bit. But what people realize, mathematicians studying it, is that this is a universal computer. And actually, there is a design of the initial settings that you have to put in this game. So in this automata, we give the rules, and it can compute all the decimals of pi. And you know there is an infinite number of decimals to pi. So because we just give the algorithm and the way the algorithm is running, someone finding that should know that we have understood that there is pi is an irrational number, so a transcendental number. It has an infinite number of digits, and we have a way to compute all of them. So it tells a lot about how we think of the world without having to put all the digits on the disk. And it would be impossible because there is an infinite number of digits, and we are able to stack something which is infinite on a finite disk. Yeah. And this is what the use of mathematics are made for. And if you find this, maybe you would not know everything on humanity, but you will have some ideas about how humans were thinking today. And you were talking about the Grotte Chauvet, and I know some people who have been working on the Grotte Chauvet, and they look at the drawings and say, you know, to make such a drawing with something which is going like this way, which is consistent, it means that these people who have been making these drawings, they had some kind of cognitive level in the way they can think the world, the way they can see the world. And this is what we want to say, because we are here today, and maybe we can think, because UNESCO is in the game, that once one of these discs is done, you can imagine that every 100 years, there is a team doing this, and you pile them on the moon every 100 years or every 500 years. I don't know if we manage to go that far. And such an archive will give you an evolution of the way humans have been thinking over time. And that could be something great if, I mean, for future archaeologists or future, I don't know what, alien archaeologists.
So we have 100 billion that are going to be spread on 24 discs. 100 billion pixels is a lot. But still, it's an awful amount to summarize, you know, what needs to be safeguarded for the far future. But I think it's the, I think it's a very compelling and very fun way to put yourself in the position of, you know, what if I was to safeguard something, like for me, but for all over the world, and I tend to put myself in the shoes of Jean-François Champollion, who managed to decipher the hieroglyphics back in the 19th century, and I can try to imagine the excitation, the excitement that he had. You know, translating all the hieroglyphics from hieroglyphics to French, and because like there was a whole world, a whole lost world that appeared in front of me, and that was the world of the ancient Egypt. And I think that putting yourself in that position was going to be common with our descendants in the long-term future is the same excitement for curiosity. And when they would say fiddle with sanctuary, they're going to be excited. Oh boy, they're going to be excited.
Yes, because of course we have been talking about aliens, the future and so on, but for me, and I think we discussed that a lot with Benoit and the team, this is important for today. Because the content of the disk will be released, I don't know in which way, once it will be on the moon, probably website and so on. And actually this is a marvelous pedagogical tool. You can take one of such disks, give it to kids in a high school, for instance, and say, okay, let us study the content of this disk. Let us make lists. What is there? How is it written? What is missing? And then, you know, this is all this book you find sometimes with like statistics on the size of the mustache of dictators or whatever, all this kind of stupid knowledge, but people enjoy it. And then they start to discuss, did you know that the animal that kills the most human is not sharks, it's a kind of medusa, and this is how knowledge is flowing. Imagine you take this disk, and you give a school and another school, and they can study it, and they can meet, and they see what they have discovered about the knowledge we have today. So this disc, of course, they are talking to the future, but they also are talking to humans today here on Earth. And they tell us, look, guys, this is what we know today. And probably in 50 years, if someone is doing the exercise, say, oh, but this is not there. And they say, yeah, it's not there, because 50 years ago, they did not know that. Okay, when you take books in the library, of course, it's interesting to know what you find as knowledge in the books, and you learn something, but sometimes you say, but they didn't know that? And then you realize that, of course, this is something that is not just from 10 years. And we were talking about astronomy. I can take books I wrote 20 years ago, and I say, well, there is a lot of things missing there. And if we are giving a book to someone, you say, well, this is out of date. And this is also what this is important, and it can be used for pedagogical reasons in schools, and also to give conferences about the universe and to tell a lot of story. And as you said, you have to go inside. It's not a list. There is not a table of content of what is in it. You have to explore. And I think this is what we want to do, is that people are engaged to to explore knowledge by playing with this disk. And to that, I think this is a marvelous tool to be used.
But again, like of course we're having fun, but there is there's a huge amount of, I mean, like people got serious. Like here, the maps, celestial maps of constellation. All the maps have been curated by Michael Benson in the US, who wrote like a compelling book about how humankind saw the sky, and you know, what kind of maps it drew of it, what kind of artwork it did. And I asked Michael, you know, what are the 15 different either maps or drawings from your book that should be selected and be safeguarded for eternity. So here's one of them. There are a few others here displayed here and there. Here there's something that I kind of like. It's you know, power of 10. I believe that it's part of. There's a similar video displayed at the Cité des Sciences.
Yes, power of 10. It's called. It's on the internet.
Here we have the location of all exoplanets known. And here is the list of all exoplanets known. When was it?
Yes, you have to put it.
So it needs to be updated because there are constantly new exoplanets being discovered. And there's this first part of the triptych that I'd like to show, of course, is the genome. And it doesn't look so appealing than the two other days that I showed you guys, but it's something that I knew that I wanted from the very start of the project. It was the difference between now and the 70s, and one of the main difference, not trying to reinvent the wheel, is the knowledge about the genome. So I contacted Martin Krasinski, who's a geneticist in Vancouver, and I asked him, you know, is it hard or is it simple to get a genome? He told me, well, you know what? Of course, you need some kind of ethics board to review all of this, which we had. So we had, I believe it was 30 male patients, 30 female patients, and one patient of each group had been selected in a double-blind process, meaning that neither the doctor nor the patient knew who was who within the process. But this is half of a female genome. I'm not sure if you know too much about DNA, but DNA is comprised of 4 bases: A, T, C, and G, and A is always combined with T, and C is always combined with G. And well, you saw from the 2 previous discs that the content that is engraved on our disk is analog. Here, it looks like shades of gray, but on the close-up, we have dots, and we have AT and CG that are being, combined, and it shows so half of a female genome. And you're going to say, you know what, good for you. You have half of a female genome, but how do you do that? How do you combine, and how do you decipher all of this? Well, we also included some kind of user manual on how to combine the genome. So here we have a small phylogenetic tree showing all different species, and here is a way on how to use, so to say, the disk of the human genome. So how do you combine together? But there's another statement that is there are a few others. It's a philosophical breakthrough. It's just like, of course, the genome is super important. Say if it was my genome or the genome of a different male, the visual difference between my genome and the one of an Ethiopian, of one of a Peruvian, of one of a Chinese is only different by the range of 0.1%. So meaning that visually you wouldn't even see the difference between this disc and the disc of someone else. And this is it says something. It says something. Well, and the other thing that I love to say about this is those discs are going to live with the Artemis program. And Artemis program is the follow-up of the Apollo program. And Apollo brought 12 men on the moon. And with the genome
White and
discs,
American.
and 12, so with 24 discs and 2 human genomes, knowing the difference of 0.1% per humans, of difference in DNA, I mean, we're bringing humankind itself and the biological recipe of humankind itself on the moon, potentially forever. And we're not trying to say that it's some kind of backup for apocalyptic times. It's just it will just be there. It's just be there. And we can do it, and we think it's the right thing to do. In history, I mean, like, we are the first species that would be able to safeguard its biological recipe for eternity on the surface of another world. Who knows? And this is, there's hope in it.
Yes. And the genome is not enough, because you can give the genomes, you cannot make a human out of a genome. You need to know a lot of other things. And as you showed on the movie, on the other discs, they are like the evolution of the embryo. There is a lot of things about anatomy. There is all these things about biology that allows you to know what these things are. And of course, we can dream that, like in Jurassic Park, for instance, you find this and you get high technology. Why not? You can relaunch humanity from this. This is not the goal, but we are aware that, just giving the genome will be a reductionist view of humanity. This is kind of a chemical formula which is very long and very complicated. It's more than that. We know that it's not enough, and this is also what is described on the other disc. And this is why it was very important to have, all the anatomy, to have all the organs, to have the evolution of the fetus, to explain that there is a whole process, and biologists know, that the genome is not enough. This is a signature, but it's not enough to make a human.
Exactly, and it's also a profound statement. If we were to have Jean-Philippe's DNA on the disc, and potentially there could be a clone of Jean-Philippe, but Jean-Philippe cannot be reduced to some kind of of DNA.
Because I'm not grey. That's the reason.
I mean, like, it's experience, it's love, deceptions, and everything, and this is. And being sensitive.
No, but this is why you have the culture layer, which tells you that there is also this culture inheritance, languages, and all the things we are doing, and this is not coded in these things. So this is also, we had this strong discussion, and this is also my belief as a scientist, that reductionism, which was very popular in the end of the 20th century, is not working. I mean, we have a lot of instances in science where we know it's not working. And also you should give also, like, all these small squares that you see here and there. Yes, we have a lot of drawing by kids. Okay, and this is also, we went to hospitals, and there are kids in hospitals, and they're drawn. I mean, this is Elsa, who has done his space shuttles to go to the moon. And I think this is also that we wanted to have, this is not science, this is not knowledge, but I mean, we have all been drawings, and not only artists, from the smallest kid, he starts by drawings, trying to make, a man or a woman, and we know it's a long process. And all these things make us human, because when there is a kind of, in the imagination of all kids, and they didn't know each other, it was in different hospitals, different ages. I even got some of them from Africa, and they have this image of what is a space shuttle. So the image of a space shuttle is a cultural knowledge of all of us, even if we are not scientists, if we are not interested in space research or astrophysics. And this is also what is culture, and to me, this is also what these discs are about. It's kind of the scientific part of science, which will be common culture in some sense. And the genome has to be common culture. We should all know something about the genome. We should all know something about our position in the solar system, in the galaxy, because we live in such a world. And if you don't live with the knowledge of today, you are outdated, and you cannot face, all the problems we have today on Earth. And we have things about climate change, rise of the ocean, and so on and so on.
Yeah, so it's still an ongoing project. So we will have we have more discs, you know, that will be designed in the next few years. What is going to I'd like to get back to what you said. It's to what you said, Jean-Philippe. I think it's it has never been. Yeah.
So this is the petit cueilleur d'étoiles. For those who are from the French Astronomical Society, this is a group of people who are going to hospital to talk about the universe and the Earth to kids in hospital who have cancer, so we stay a long time in hospital and they make projects in hospital. So this is also, we wanted to show these different things.
So it's not. Yeah, it's a very humble project. It's a very humble project, and when you start to know that you can't bring everything, you know, you know that it's that you're never ever going to make something, say, grandiloquent.
Yes, but we had to go through this at the beginning because when you start, you want to be not perfect, but to, you know, you said it's a huge amount of pixels and possibilities, but you have to know that you are limited. And as humans, this is the first thing we have to learn. We are limited. We are limited in our body, in the time we are here on Earth, the things we can understand. We are always limited. And to accept the limitation we have in all the things, this is a way to be human also. We are not a computer. We are not whatever. We are humans. And this is, for me, also something important. And in the process of making the disc, we had to go to different steps of saying, okay, this we cannot tell. There are things we cannot tell. And, well, this is part of the game, and because it's not there, people could criticize, and this is also why it's not a pure encyclopedia. It's not. It's just sanctuary.
It would be anyway open to comments, but when I have, you know, when I have this kind of fear stirring up, when I feel them, I just tend to reassure myself, saying that, you know what we brought. At least 2 full human genomes. I mean, it's worth the trip.
Yes,
it's worth the trip, and the adventure is marvelous.
The adventure, and also as you have seen, like even the non-knowledge, they are designed in a graphic ways. So, and if you look at the disc, I mean, we can discuss that. I found them beautiful, and I say, okay, it's not perfect, it's not complete, but you know, this is like a piece of art. It's also a piece of art. It's science. It has a lot of contents. It has its genome, but it's also a piece of art. And I think when you do art, you don't question the fact of being, you know, complete or whatever. You say what you have to say and what you can say. And I think to me, this is also a way to evade this question of being complete and to say everything, because you do what you can do. And this is also, I mean, as we said just before, it's the single thing human can do. We just can do, you know, imperfect things.
And so there was, so we talked with Jean-Philippe about Rosetta Stones or alphabet. I asked Martin Krasinski if there was a way to encode sound and music
Yes.
under this. So visually, try to, you know, visually encode sound, and we found a way to encode sound. So meaning that we are opening the disc for future music contents. So we have a full spectrogram of I believe it's either Swedish or Norwegian band called Flunk, and so there's 3 minutes 30 seconds of that track here, and we have a Rosetta Stone on how to decipher the spectrogram and play it back.
So you see, this is you have time here, so why it's important to know what is a second, and you have frequencies. So basically, this is a sonogram or spectrogram, as you wish. And basically, if you go this way, you have like the frequency content of the sound that you have. So basically, this is basically the way, if you take this information content, this is what you have in an MP4, for instance. Okay, so you don't have the full sounds, you will never be able to have all the frequencies. This is sampled, but then you can represent it graphically. And if you have the tools, I mean, to transfer this image into sound, and we give all these things here, the details, because to transfer that into sound, it also means that you need to have an understanding of what is the human ear. And also the atmosphere, because if you change the atmosphere, you put helium here, all the frequencies will be shifted, and there is a cut. You know, we know that human ear is going from 20 Hz to 20,000 years.
20,000.
Yes, from 20 Hz to 20,000 Hertz. and so on and so on. So you know that you have cut some kind of frequencies, and resolution in different frequency bands are different. So this is adapted to the human here. But once you know that, you can play it and you can listen to it. So this is.
But this is a better version of the. Also, we should
Yes.
get an improvement. Oh, by the way, UNESCO requested that on the genome disks, just like the science disk, here on the outskirts, we're not going to put the Universal Declaration of Human Rights, but something that is very important for UNESCO. And I think I never knew that it existed. It's the Universal Declaration of the Genome, meaning that no one can appropriate itself with the genome. And yeah, so that's it. So there's going to be another Rosetta Stone on the outskirts.
Yes.
I am going to finish by showing you, well, you know, this.
Je te laisse maintenant. Je vais me rasseoir. Je suis fatigué.
So sanctuary will be placed in a container attached here. So we made some kind of rendering. Here you can see it like the hexagonal shape of a space probe. And we asked NASA, I mean, it's still in discussions, to be placed on a mission for which a rover would be deployed on the lunar soil so that it can make some kind of U-turn and take a picture of sanctuary placed on the probe. And finally, I'm going to end with this quote that I love. And this quote is 4,500 years. It says it all. And for those, I brought a disc. So, and if you guys want to have a look at the disc, you're more than welcome to come here up close. But be gentle with the disc.
So, thank you a lot for this very interesting and maybe a bit less scientific, but very like humanistic and really interesting presentation. Maybe we have some question here concerning the, yes.
How do you show which order to deduce the human genome?
How do I what? I'm sorry?
How do you show how to read the genome?
Okay, it's within the user manual with arrows. Of course, you're going to tell me, you know, who knows in like 100,000 years or millions of years, you know, what direction an arrow would mean. But you still have to make assumptions and guess. So you have like some kind of path of pixels. And there's another thing that I didn't mention is that the genome, so we even took the liberty to send some genome graphically sequenced to a lab to know which would be the most accurate engraving. So the machine could engrave from 1 micron to up to 1.5 micron. And we found that for the genome, if you don't want to have many mistakes, you have to go from 1.2 to 1.4 microns. So there's no mistake within the whites and the blacks, the AT and the CG. Plus, there's also a correction grid that is like a giant Sudoku saying, you know, on this row, and on this column, on this row, you have that amount of black, that amount of white, that amount of, and so on, meaning that if there are errors within the genomes, it can be corrected.
Thank you. Any other question, maybe? No, so, oh, yes.
Thank you for presenting your very interesting project. And I think your methods and your process of creating these discs is as much as important as creating this for the future. And so I was wondering, how did you work between all these people? How was it hard to bring all these people together to create those discs? And also about the interdisciplinarity between scientists and maybe other fields like sociologists or social sciences.
So how do we work? The first thing was, I stumbled upon a book called Murmurs of Earth, written by Carl Sagan about the making of the Golden Record. I'm a producer, but I'm a former journalist, and I'm reading this book. I always thought that, something was missing from the Golden Record is the making of. I would have loved to see Carl Sagan, going from places to places, and hence your question, how do we work? And so basically we got inspiration from, how you proceeded. It's just like an informal team of, I wouldn't say, experts. I'm not an expert. Jean-Philippe is an expert in astrophysics, and it all begins with the science. When you want to convey stuff for the far future, you need to get to irrefutable stuff at the very beginning, and irrefutable stuff, it needs to be told. And then, from what needs to be told, you can say about art, you can tell a lot about art, about life, about a lot. How do we work? So we had like different workshops that are organized in Paris and the outskirts of Paris, where there was there's a graphic designer who would take notes from the discussions we had with geneticists, paleontologists, particle physicists, astrophysicists, you name it. And from one workshop to another, there were iterations of the graphic design. And so it took quite some time. I'm not going to hide that the first 3 sessions, when you start with a blank page, that was one of the most stressful time of my life. It's just like, what am I doing? What the hell am I doing? But there's something that I need to stress out, is the fact that when you start working with constraints, the science, the language, what that needs to be absolutely be included in the discs, it gives you a frame, and then a framework, and then you add more constraints, and then you're getting more and more creative within this frame of constraints. And constraints are virtuous when it comes to that kind of process. But I believe that Carl Sagan had the same feeling. It's just like you have a 33 RPM record. Well, you can include images, not so much, 100, and you can include sound, and that's it. What do you put? Nobody's going to tell you that you are an idiot because you didn't include some, I don't know, Vivaldi. Including Bach, Mozart, and Stravinsky is already a very nice feat. So that's it.
Yeah, and and also, what is important, you see, he shows the people of the team. So we needed to have some people with different knowledge, but not a team with 100 people. what you would learn from project is that if you have a reduced team, you are sure that first you can discuss a lot, and people there in the room, they really work, they really produce things. We had some issues. I mean, we tried to propose to different people to join the team. They came to one meeting, and then they realized the amount of work that it is to do such a thing. And then, of course, as you said, the first session, they were really difficult because we were looking for our language, this graphic design language, the topics of the disc, nothing was there. And we were just, I think, 4 or 5 at the beginning, and Martin Krasinski, Roland Lehoucq also, he has been doing a lot with, he's an astrophysicist, but he has all this knowledge about science fiction, and this is also related to some kind of science fiction idea, I mean, doing such a thing. And I think it helps a lot. And once the language was there, and you know, the graphic designer Mario was hired, we found a way that each one is making some what we call stories. So basically, this is a piece of knowledge. We have some sentences, we have data, and we have some kind of basic ideas of how to present them. And we were passing that to Mario. He was creating some graphic design, and then there were iterations. This is a lot of work. We were not sure this thing will fly one day. That's also something. So we were working, and we didn't know. I mean, there were some hope, but it was going ups and downs. And when you ask people to work and to come to workshop, but in between workshop to produce things, work at night and do these things, then they say, well, either I don't have time, or there are limitations. I mean, remember we met people from the Louvre who wanted to have a collection from the Louvre and say, but you know, if you pixelize this drawing or this painting, we cannot do that. They had some kind of barriers about the fact that we would put this on the discs.
Yeah, and the other limitation is the fact that the discs are monochrome.
Monochrome,
so
yes.
when you want to put artworks, when there's a way to encode colors on the disc by putting RGB pictures in shades of gray, in intensity of shades of gray. So you have like intensity of red, intensity of green and blue, and then you combine all the 3 pictures all together. But putting 3 pictures, you miss space. So we can do that, but to a certain extent.
Yes. So you see, there was no recipe. We just did it in this way. Probably we could have done it differently. We could have included other people, because we didn't say, who is want to, if we went to the radio or the TV saying who is wanted to do that, we will have like 1,000 people who wanted to participate. But then how do you make something which has an identity if you are 1,000? So this is a balance between the two. But I think whatever you create in life, it's always like that. You start to discuss with the people and we had this small community of people who are both scientists, but they like also to do outreach activities, which means they like to talk to the public, and they are interested also in art and in science fiction and so on. So they had the good profiles for that. And then we went to take some specific expertise of people, because now that it exists, I mean, there are a lot of people who want to contribute, and this is the problem.
Yeah, but the better is the enemy of the good. Huh?
Yes.
I mean, like. As you said, from our experience, it's. I think it's. I mean, I'm glad that many people are willing to contribute. But the thing is, there are so many constraints that I'm trying to, just be like a mouse within a trap, because nobody sends stuff to the moon on a monthly basis. I mean, I wish I could. Just the thing. This is also why space is so expensive. Is because it's the very fringe between. Huge industries and craftsmanships. And what we are doing is craftsmanship. We are doing low-tech object with high-tech. And we have different, I would say, inputs from experts. So if we have too many inputs, things could go nowhere, and we like to keep and there's no right recipe in making the perfect project. It's just like trying to make things afloat, so that the very spirit, the very intention of Sanctuary will be brought to the moon. And we hope that if someone is not moved by the fact that we brought 2 discs with DNA, they're going to be moved by the fact that I love chess. They brought like a chess game with the rules, and I'm not into exoplanets, but you know what? They brought anatomy, and I want to be a doctor. And this is how you can position all the discs all together so that you can see the whole full human anatomy. And this is, it's like planting a seed. Planting a seed and I hope in a lot of people. And there's a quote by Carl Sagan, by the way. And this is something that we haven't discussed. So, sometimes it's just like, yeah, but who's going to find sanctuary anyway? There's a very high chance that it's never going to be found. And I tend to agree, but this is what he said about the pioneer plague. There is only an infinitesimal chance that the plague will ever be seen by a single extraterrestrial, but it will certainly be seen by billions of terrestrial. And it's also a purpose of sanctuary. It's just like not making some kind of time capsule for the far future, not only, because we'd like the content of sanctuary to be, I don't like the verb, but exploited, but like in conferences, exhibitions, concerts, coffee table books and so on. The whole content of, say, the science discs are going to be made available for UNESCO. So UNESCO will be able to take from it, and display them in leaflets, brochures for kids and for others.
Yeah. And if you are not interested in that, we can have Pac-Man and Donkey Kong also. So there are a lot of surprises, so you'll discover that soon.
A big thanks to both of you for this amazing presentation. And now, just before the last lecture of this Congress, maybe Jean-Philippe Usan, who is the patron of this event, would like to say some last words before going.
Si tu veux.
Plaisir.
Okay, so I think what I've seen from Friday to today, I think it worked. It worked because when Alexandre, Merlin, and all the team started, you started both to have this idea because I think last year you had this online version of this international conference. And, I'm part of the French Astronomical Society, and that's one of our ideas to develop astronomy and science in all possible ways, to create bridges between professionals and amateurs, to develop astronomy in many countries, and to try to have no border. And this is why we are going to hospital. We do a lot of activities. But such society, sometimes they start to become older and older. And a couple of years ago, with Sylvain, who is now the president of the society, we decided that we have to do things for the youth because we know, this is a problem of transmission. We have people studying at schools and universities, but it's not enough. If you want to go to this job, you have to meet people. You were in astronomy clubs, but it's not enough. You have to meet professionals, to ask questions, to have this kind of in-between talks, which are not popular science talks that you can find everywhere, but which are not lectures. And I think this is a good combo. And as I said yesterday during my talk, I hope both of you'll take time once you are home to write to us and to say, okay, this I liked, this was too difficult, I have this kind of ideas, because I think this is something you are going to develop. It's the first edition, so it exists. So congratulations, you have managed to create that, it exists. I think it was a success because you managed to have people coming from, I don't know, how many countries? 14 countries, so it's something important. We want, in my belief, science and knowledge is something that has to be shared with everyone, not only in one country. So the fact that it's international is very important, and I hope, and this is for me one of the key points of science, all these big collaborations, they bring some kind of idea of peace. We collaborate with people, men, women, older people, younger people, from any religions, any culture, and this is what we want for science. Science belongs to everyone, and we have to share it. So this is what we can try. We will help you. We had sometimes, as I said on the first day, you had too much ideas, you wanted to do too much. And sometimes, as for the disk, you have a limited time, so you need not to address all the questions. There are a lot of questions in astronomy, exoplanets, and so on you wanted to talk about. It was not possible, but this is good because there will be other editions with other topics, and I hope it will continue. And this is just the first launch, and we will have, in a couple of years, the chance to say, okay, this is the 10th edition, and probably you will become, I don't know, PhD student or researcher, or some of you here, and you will participate to younger people. So don't forget that doing research and studying is a nice thing, but we all are teachers also, because we got a lot of things from our teachers, and we have to give back, and this is the best way to give back. We teach, we do outreach science, but also we organize this kind of meetings. So thank you to both of you and all your teams, because it was very active and successful, and I do hope it will continue like that. And also I do hope that, you know, some of you are in the audience today, you will probably join to participate with them, because I think you need relay in other countries. We can even think that, well, it has been in France now, maybe it could be in another country another time. I think it's also a chance, because of course local students, it's easier for them to come. So if we go to another country, it will attract people from, to do more dynamics in other countries. So I think we are completely open to that.
Exactly, we are completely open, and you said all the things.
Thank you.
We were aiming
because
to.
I'm old and new to this kind of thing. So the last word is I want to thank you all, and I hope that you keep in mind that sometime, you know, in life, and especially today in France, we are all worried with many political things, that science is a place where we meet, and we meet because we want to understand. And there is no political issues on that. We want to understand the way the world is working, and we do that together. Of course, there is competition, and you will see that sometimes you want to finish the article or make the discovery before. It's a good competition. It's just we want to manage to do it. But most of all, what I've learned from doing research for 30 years is you make a lot of friends. You make a lot of friends. I have friends who are older than my father. I have friends who are younger than my kids, and we work together. And I have friends in many countries in the world. And I think this is what you have to keep in mind. Love learning, love discovering things and sharing them with all the other, because, you know, knowledge has no price. If I give you my knowledge, I still have my knowledge, so this is infinite. It's not like energy, it's better than energy. So I think all has to be based on knowledge and the sharing of knowledge. So thank you for, you know, having us going this way, because of course I don't think neither of no one in the French Astronomy Society would have thought about doing this and having this energy to carry it, because it was difficult, you know, to find the room, to make the program, to have all this administrative problem. But this is life. Life is also administration. We don't have administration in the disk, by the way. And I think this is you have learned a lot from doing that, because this is also part of scientific life, to organize things. So thank you for having the whole community be able to have this creation and this talk. And I hope we will have another one very soon.
Yeah, next
Thank
year.
you to both of you.
One. And thank you, Jean-Philippe, for your support.
Thank you.
Thank you.
Bon, à bientôt. À très bientôt. Nous, on doit y aller parce que...
So thank you Jean-Philippe, thank you all of you, and thank you to the team. So now, in the last lectures, in the last day of the event, we talked about the European Extremely Large Telescope, the ELT. And so we have here Camille Frappoli, who is the lead engineers of the designing of the mirrors on the scope. And so he will give us some insights and a presentation about how we made the mirrors and about all the, the more, technical and engineering parts of doing science. Because as Jean-Philippe said yesterday, theory is a very good thing, but without experimentation and instruments, theory will lead us to nowhere. So thank you, Camille.
Okay. So I'm starting now. So I'm Camille Frappoli. I work for a company called SAFRAN, and today I'm going to present the work we've been doing for many years now in manufacturing the optics for the extremely large telescope. And in today's talk, I will focus on the M1 mirror. So on the mirror you can see on the picture here. So and I'm going to explain you how we make these mirrors and why it's important for ELT. So first, let me introduce SAFRAN. So we are a company founded by French scientists, including Charles Fabry, so the guy from the Fabry-Perot, and Henri Chrétien, guy from the Ritchie-Chrétien telescope. We were founded more than 8 years ago. Nowadays we have a bit more than 40 million in revenue. We are about 170. We are located in the southern suburbs of Paris, near Fontainebleau, near Corbeil-Essonnes actually, if you want to know. Since the 30s we've been polishing optics for the scientific communities. We have polished most optics for European telescope, including VLT. So we have polished the main mirrors for the Very Large Telescope in Chile. Also the optics for GTC, Grand Telescopo Canarias, which is the current largest telescope in operation. And now we are working on ELT. We have also a strong activity in space optics. So we have been polishing the optics for Gaia, Euclid, and NearSpec for JWST. So what is ELT? So here you can see the site in Chile, in the Chilean Atacama Desert, in high altitude, so it's important to have the best seeing. Here you can see a render of the ELT. On top, you see it's on top of the mountain. It's important to be at high altitude to have the best image quality on telescope. You can see opening the dome, a peak on the M1 mirror we will speak about here. It's the reflecting hexagonal panels. You can see the telescope moving. So here is the optical structure of the telescope with M1, M2, and M3, so forming what's called a three-mirror anastigmat, and then M4 and M5 are used for adaptive optics to enhance the image quality during operation. And the light goes to the instruments that are on the what's called the Nasmith platform here. So instruments are, if you wish, the camera for the ELT. But these are very expensive and complex cameras, so we call them instruments. So this is the same image. So the primary mirror you see is on the bottom. It's a 39-meter diameter mirror. When made, it will be the largest primary mirror for a telescope. It will be the largest telescope in operation. It's built by ESO, which is a European Southern Observatory. It's actually a European organization with, so I look at my screen here, 16 member states. I think maybe there's more now. They basically handle the operation and the data of all telescopes in Chile, in the Atacama Desert. Now they are undertaking the construction of ELT, and it should be finished by 2028. So like I said earlier, ELT has a gigantic primary mirror, but also very complex other mirrors like M2, it's a 4-meter mirror, convex, probably the most complex piece of optics ever built. Then you have M3, also a 4-meter mirror. Then M4 is an adaptive mirror. So in a telescope on Earth, you have the atmosphere that kind of spoils the image quality with turbulences. So the quality of image that you can get from any telescope is called seeing. And it's better in high altitude and in some site where you have very stable atmospheric condition, where you have low humidity, which is why the telescope is actually in a desert. But still, you still have let's say, a limited imaging resolution that you can achieve on Earth. And to improve on that resolution, there have been techniques called adaptive optics, where you have a deformable mirror with thousands of actuators working at hundreds of hertz. And ELT has one, it's M4. So it will be the largest adaptive mirror ever made And so you see it there. And finally, you have M5, which is a pointing stabilization mirror. It's also very hard on such a big structure to have a super stable pointing. And so the image kind of vibrates. And to compensate the vibration, we have a very light and stiff tip tilt mirror to compensate for the pointing. Now I would like to comment a bit on this image that you see here. I think it's very important to understand what it means. So on the left part, you have a telescope in operation at the moment. In green, you see the telescope from the Atacama Desert in Chile. And in blue, you have a telescope in Hawaii, which is the other exceptional site on Earth. So you see these two sites concentrate the most telescope today. And on the right, you will have the next generation of telescope currently being built. So you have ELT here, GMT here. Both will be in the Atacama Desert. And you have TMT up there. ELT is a European project. GMT is mostly US-led. And TMT is led by US, India, and Japan. And I like this image a lot. This is from Wikipedia because it shows you how much of a breakthrough this next generation of telescope will be. You have to imagine that only ELT has as much collecting area as all other telescopes on the left part of the image. So when you build ELT, you effectively double the light collecting capacity on Earth. So this will be huge. And another annotation that you can make is you see that REOS contributed to most telescopes on Earth today, and we are very proud of that. So I see a very young audience. If you'd like to contribute to the engineering side of the astronomy, think of us when you have finished your study. Here I will show you a few pictures to see how ELT advance. As I told you, it's planned to be finished by 2028, so it's very well ongoing, if you wish. So this is a picture from the end of last year, I think, and you can see the site. So you see it's really a desert. And it's very important because first you don't want any light pollution, and then you want a very dry and clear sky area. So this, actually, I think you have 360 days of clear sky in the Atacama Desert. So that's as many nights of observation available. So the mountain has been flattened. So the top of the mountain you see has been flattened. A road have been built, and you see the dome has progressed quite a lot. Today you really see the ELT being built when you are in Chile. Viewed from the side, you see it's a very big building. To give you a sense of scale, so this is a typical loading cargo dock, so to say, so it's really big. This is 40 meters high. So this is a many-story, it's not really a skyscraper per se, but it's a many-story high building, so it's huge. I think this is the most recent picture, and I like it a lot because you can see two things. You can see first the alt-azimuth mount that start to appear with the bed of the tilting mount. And also you can see the sky up there, and you can see how clear is the sky as compared to what we have here. And finally, so okay, you can see it on the internet. Here you don't have as much contrast, but you can see a very nice picture of the ELT taken from the site of the VLT. So you can see ELT is, I think, 40 kilometers from the ELT site, so you can take very nice pictures like that with a long focal length objective. So, back to the mirrors. At REOSC, we polish all the mirrors for ELT, including, so today we'll talk about M1, but we also polish M2. So, as I said, it's a 4-meter mirrors. So you can see people here for scale, so it's really big. It's like 4 meters in diameter, it's 200 millimeter in sag, so this is 20 centimeters. And the figure of merit for complexity in optics is the departure from base sphere. This optics has a 2 millimeter departure from base sphere, which is unprecedented. You have M3 up there that will be polished after M2 is finished, which should happen by the end of the year. Also, a figure that you have to keep in mind. When I started at REOSC about 6 years ago, we are just starting on M2. So you see this kind of optics, it takes years to complete. It's really an engineering feat because you have to make a lot of work on what goes around before you start polishing. So that's why it takes such a long time. So here I talk to you a lot about adaptative optics. These deformable mirrors. So to have a deformable mirror with high accuracy, you have to make what's called thin shells, which are thin sheets of glass. This is 2 millimeters in thickness and quite big, and this is a key element for this adaptive mirror. So this is a thin shell for ELTs that we delivered last year. We delivered the last one, we delivered 12 of these to make a huge 2.4 meter adaptive mirror. And finally, the last received at REOSC is ELT-M5. So you can see it's also very big. It's 2.7 meter in its largest dimension. It's elliptical, actually. And you see it's a slightly different material. So on the left, you have glass ceramic, which is slightly yellow. We'll come back to that in the next slides. On the right, it's a black material. The material is a critical part of making an astronomical mirror because when you are in the desert, the temperature might vary quite a lot. And to have the best image quality, you have to maintain the shape of the mirror. So actually, it's very important that you have a very stable material. So the most stable material is called Zero Dur. It's made in Europe as well. And it has this yellow hue here. Another very good material is the one that you see here, and that's kind of black. It's called silicon carbide, and that's the second hardest material on Earth after diamond. It's very difficult to polish, but it has very good characteristics in terms of it's very light, it's very stiff, it has very good thermal conductivity, so it's a very good material for optics as well. But it's super hard to polish. So, okay, here is ELT-M5. Okay. Back to M1. So, what is M1 if we go more in depth on its characteristics? So first, you see that the M1 is a segmented mirror. So it's 39 meters in diameter and is composed of 798 hexagonal segments. Because these are hexagon, you have a nice symmetry property. So actually you can divide the mirror in 6 identical sectors, a pie chart if you wish, and each sector has 133 mirrors. Each of them is different, which makes it very hard to manufacture because you don't manufacture actually 800 identical mirrors. You manufacture 7 times 133 mirrors. So why 7? Because you have 6 sectors that you have on the telescope and you have a 7th one spare. Why you need so many spares? It's because on the desert, when you coat the segments, the coating, the reflective coating, the silver coating that you put on top gets damaged over time and the reflectivity decreases. So every couple of years, you have to recoat the mirrors. This is true for all telescopes because you have dust, anything that comes on top. And you have 800 mirrors, and you have to recoat them every 2 years. So you have between 1 and 2 mirrors every day getting coated at ELT. This is unprecedented. Usually, it takes many days and so on. At ELT, even the operation will be industrialized. So that's why we have to do so many spares. So a single segment is 1.4 meter corner to corner. And when I say they are all different, they are not slightly different. They differ by several centimeters on their edges. The surface also is also different from segment to segment. So actually, what the difficulty of a segment consists in is a departure from base sphere, the asphericity. On ELT, the asphericity is typically the size of the Montparnasse Tower, or 2/3 of the Eiffel Tower if you prefer. And the residual error on this shape is the size of a ladybug, and this if you scale the segment the size of France. So in real numbers, this corresponds to about 7 nanometer on a segment and 300 micron aspherization. So if we put it on real scale, so this is the typical error we put on a segment. So you see this is 50 nanometer. This is 1/1000th of an hair to give a scale. And here you can see the scale of a coronavirus. This we know. And you see the defect is much smaller than that. It's actually more or less the size of protein. And if you look at the local roughness of the mirror, it's more the size of a molecule. So it's a really precise surface to be imprinted, and it's a complex surface because you have to imagine this kind of accuracy has to be reached with a very complex shape to the order of millimeters. And also what's very complex for optics, and this you may not know, is that the surface is not quite flat. So this is very difficult for opticians, and also it has to be polished up to the very edge, and this is very difficult when you make optics. But this is more the technical details, I won't bore you with that. How do we make that? So we start with a blank of zero dur. So zero dur is a glass ceramic. It's very close to what you have on your cookware, on which you put your pan. And its critical property is it has near zero thermal expansion, so it doesn't change with temperature. And this is really important to have this precise material because when you engrave a super precise shape down to the nanometer, you don't want the shape to be modified when you put it in the desert at 9 degrees instead of 20. So it's super important to use that material. It's a very, very expensive material. Just to give you a sense of scale, a single blank like that is worth between, depending on inflation and so on, between 40,000 euros and 70,000 euros these days. So it's extremely expensive. So you start by gluing some pads because the mirror is typically held on the telescope through glue. We'll come back to that later. Then we imprint the proper shape, the ones that will make sharp images, by polishing. And since you can only make what you can measure, we have a strong metrology to assist the polishing. Metrology means measurement. That's the instrument that measures the shape of the mirrors. Then we cut the mirror from its circular shape that you see here to an hexagon that you see on the left. Sorry. Then you put it on a mechanical structure that is active. It's actually a structure that can warp the segment during operation of the telescope. And you finish the optical surface down to a few nanometers using ion beam figuring. We'll come back to that later. Here is a short video of what the plant looks like. So it's in Poitiers. It's near Poitiers in western France. A typical segment takes between 2 and 3 months. This is typically 5 to 10 times faster than a typical optics this size. At any given time, you have between 60 and 90 mirrors in the plant, and so you can make 1 mirror per day, which is unprecedented pace of manufacturing for such a telescope. And it's necessary because it still takes 3 years to make all the mirrors of the telescope. So the first step is gluing the interface pad. You glue 51 interface pads, so they look like the top picture. So these are small bits of invar. So invar is a metal that does not dilate, because if you put regular metal on such a glass, you, with any temperature difference. The glass would explode under the pressure of the thermal expansion. So you actually need to put invar pads on the mirror. This is not your typical bond, your typical glue. This is actually a very technical epoxy bond. And you have to imagine this has to hold during 30 years in a very critical environment. It's in the desert. You have strong earthquakes. It's an earthquake zone. You have temperature swings because temperature in the desert varies a lot during the day. And these have to be transported on the Atlantic Ocean. So you have actually to make very strong bonding. Each of these pads can hold a cow. So this is a very strong bonding. There was a lot of work in making this work, a lot of calculation, and also we need to apply a process that is super repeatable. So to do that, you cannot ask a human to do that repeatedly. I mean, you can imagine you have 51 processes, 1,000 mirrors, so you have 50,000 bonds to make, so it's very hard for humans. So we made a machine, so it's a 15-meter long machine, and here is what it looks like. So you can see the glue is on the blue syringe on the right, and it gets injected between the pad and the mirror. And while it's injected, you have a camera below that you can guess here that monitors the growth of the glue joints, and that's how we ensure that the glue is of the best quality. You can see the syringe here. So this was a very hard machine to make, very fascinating, the challenges that you find in such seemingly simple task. Okay. Once it's glued, we start shaping the optical surface. So here, I put a small introduction in how we shape optical surfaces. So what's called CNC polishing, so CNC for computer numerical control. So the basics is you have loose abrasive in a suspension, in a liquid suspension. So what we call the slurry. So you see you have basically abrasive particles similar to what you find in sandpaper, but in a liquid. And then you have something, so either the part or what's called the pad up there that's rubbed against the surface with a slurry in between. And it's called CMP, chemical-mechanical polishing, because you have both let's say, mechanical abrasion going on between the abrasive and the surface, removing material in a controlled way. And you have also a chemical process, especially with cerium oxide, that ensure the abrasion goes in a proper way, so to say. I don't want to go into too many details. So that's the process with which you remove material. So it's similar to sanding a wooden plank, for example. But here it's with glass and typically aluminum oxide or cerium oxide, depending on which state you want to achieve. Then, in order to improve the shape, we use what we call dwell-time algorithms. So the basic principle is shown here. You start with the bad surfaces, with dips and heels. As up there, and you put your tools that remove materials, and you speed up when you have a dip, and you slow down when you have a heel. And this way you remove more material when you have a small heel and less material when you have a dip. So basically, knowing the shape up there, you can make a speed map on your part, and you can program a CNC machine to apply the speeds on the part, and then you can improve the shape from, let's say, millimeters to nanometers. And typically, the slower the process, the less precise the speed control has to be. So typically, when you start, you want to have very abrasive process with a big abrasive that remove material very quickly. And then you can only control speed loosely to improve a lot the shape. And when the part is nearly finished, you have very slow processes to attack very slow bumps and small dips. So we apply that process in many flavors. So we start with what we call grinding on a part that has a form error of several tens of microns. Then using a process called aspherical shaping, we imprint the proper shape of the segment and get down to single micron form error. Then we apply CNC polishing with cerium oxide slurry and get the form down to 100 nanometer RMS. The problem with chemical mechanical polishing is that it typically does not work well on the edges, because on the edges you cannot have uniform pressure on the part. So in order to avoid that, because if you want to have a smooth continuous surface on the telescope, you have to polish up to the very edge. So on typical optics, you leave an edge and it doesn't form an image, and that's okay. But for a segmented telescope, you have to polish up to the very edge. And the key for that is you polish a circular segment and then you cut it. And this way, you drop the edges of the segment that have a bad form. Once it's cut, you can apply a very slow but very accurate process, which is ion beam figuring. We'll come back to that later. And we finish the segment down to the 10 nanometer RMS of its spinal shape. So here is what a typical polishing run looks like. So the white abrasive is aluminum oxide. What is difficult on this kind of process is it's actually quite data intensive. Since you have 133 different segments, and on each segment you have to apply custom runs using metrology data to calculate the speed maps on the CNC machine. So you have a recipe for disaster if you apply the wrong speed map to the wrong segment. You know, you can even destroy a segment, and these are very expensive. In order to mitigate that risk, we actually implemented what we call the smart factory, which is kind of, it may seem simple, but that's actually quite innovative in the optics world. Each segment is identified by a RFID POC. And actually, it's located in real time in the plant. And then you have what we call the manufacturing execution system that schedules all the operation. It's connected to all the machines, and it ensures that the right program is applied to the right segment with the right data. We had to develop software to handle the data, so it's not using any fancy modern thing as AI, but it's still quite complicated. It does all the data analysis, it does data fusion from the metrology data, and it also tells if a process was successful or not. And then we have another program called NanoCam, which generates the speed maps, the CNC programs for each segment from the metrology data. So this is data diagram, if you wish, from a polishing cycle. So you start with a measurement of a segment, so you have the form measured. Then you have some data analysis, and you get a topography map. So this looks like this. So you see you have height. You have really a height map. It's really like a topography map on a segment. Then you generate a CNC program, and then you apply it to the polishing machine. In terms of scale, you have 6,000 programs during the operation of the plant. So you can really, really mess it up if you don't have an automated way to handle that. So, once the segment is polished, I come back to cutting. So, it's also a quite complicated process. It's critical for the performance, and it's difficult because you have 133 different objects to cut. And so, again, you have to be very careful when making all these programs. It has typically two steps. So, one step in cutting, you see the edges of the segment, and another step making what we call the edge sensor pockets. So edge sensors are a very critical element of the operation of segmented telescope. Since you have to make a continuous surface for the M1, the segment needs to be leveled with respect to each other at the nanometer level. And you have to imagine that having a 40-meter structures holding the mirrors and with pointing at different places on the sky cannot maintain nanometer accuracy in the leveling. The way this is handled by ELT is actually through active optics. So each segment is placed on actuators with nanometric accuracy, and in order to close the loop, the level of each segment is measured through nanometer accuracy sensors placed on the back. And so you have to machine these interfaces with very high accuracy because these sensors are critical for the operation and have very high requirements. So here is what the cutting operation looks like. So you see it's on a very big machine, it's like 6 meters high, and you see it uses a big circular saw. Going on the manufacturing of the segment, I would like to focus a bit on the metrology. Since you can only make what you can measure, and since these objects are super accurate, you need very accurate metrology. And since you want to make one segment per day, you need accurate and fast metrology. This does not exist on the market, so we had to develop it from scratch using heritage from let's say, former project or literature. Typically, on an optics, we measure different spatial frequencies with different instruments. The general form can be measured with what we call the profilometer, that's the object up there. This kind of instrument is very versatile, but has only a limited resolution. So we use it mainly in the beginning of the production. Then it's interesting because polishing can generate residual machining marks to measure texture on a part. For this, we use that kind of instrument, which is a stitching, what we call the stitching profilometer. It basically takes high resolution picture of the topography of the segment at many places. And finally, for roughness, for the, let's say, the reflectivity of the segment, we have interferometric microscopes. When the segment is near to its final shape, we can use different kind of techniques called interferometry, and it's much more expensive, but cannot measure bad parts, so to say. So we use it only at the end, and it has super high accuracy. It's called talisman. We'll come back to that in the next slide, but before I want to show you what the metrology looks like in real time. And just so you know, this is the most expensive part of making these big mirrors, the metrology. So this is a stitching profilometer that measures, let's say, the texture of the segment and check if it's really smooth and can make very sharp images. So this is actually a scanner to check for scratches on the segment. It's really like your document scanner, but for big mirrors. And this is a profilometer, so you can see you have many, let's say, small probes that can measure the height of the segment at different parts and can measure the form. I would like to show you a bit more the interferometer because this is really the most complex thing that's been built for this. It's a bit more specialized, sorry if it's a bit more obscure. So just to give you a sense of scale, this thing is 2 meters in diameter. The full instrument is 15 meters in length, and the tower that you see in the center is nearly 10 meters high. So it's huge. It has an accuracy with a single-digit nanometer, which is quite unique, and also it's fully automated. So the measurement is typically 30 minutes, and it requires no expertise to align. So basically you can just put a segment here, you'll see that in the video afterwards, press a button, and then you have a very accurate topography map of a segment down to the nanometer level. These are some details for the most intense of you to see how it works. So there's a video afterwards that will be simpler, but basically you have a reference optics here, which is the largest aspheric lens ever made. And all segments are compared to the aspheric lens. And then you use what's called computer-generated holograms, which looks like this, to handle the aspheric shape of the segment. And everything is illuminated with a laser to make interference on this camera. So it looks simple with this sketch, but it's very expensive and difficult to build instrument with a very tight alignment tolerance and everything. So here is a video showing how it works. So you see a segment being brought to the instrument. So the lifting was an issue for ELT as well, as you can imagine. So we put it carefully on the instrument, and we press a button, and we have a cart bringing the segment into the interferometer. So this is a tower. You can see there is a folding mirror 1 meter in diameter. This is the largest lens, aspheric lens ever made. Here, so sorry it's a bit dark, the segment self-align, and here you have all the imaging optics that are all custom made and all quite big. I think they are all like 200 millimeter optics, very hard to make. We had to make them all over the world, in the US, in New Zealand, in Germany, in France as well. We had to make quite a lot of them ourselves because no one could make them except us. And here is what an interferogram looked like. So an interferometric measurement is, in the end, is just an image of fringes and that you can transform again into a topography map. So when we have this topography map, the way we machine the segment down to the last nanometer is using another process called ion beam figuring. So the general principle is shown here. You have an ion beam that generates high energy ions that are projected onto the optics. And when you have high energy ions, you have a collision cascade of atoms, and then you have atoms getting expelled from the segment. So with this process, we can machine the segment down nanometer by nanometer very slowly to get to that kind of accuracy. So you see here, the peak to valley error is 10 nanometers, so it's 1,000 times smaller than your hairs. So it's very, very small, as you can imagine. And yeah, we move this ion beam on the segment, as you can see on this picture. Just for information, this is a kind of process that's used to make the most challenging optics in existence today, which are the optics for making chips that are made in Germany at the moment. Everything happens in vacuum, so we have big vacuum chambers as well, as you will see. So the segment is brought within the vacuum chamber. And here you can see in the purple hue from the high energy ion beam. So with all this work, we have delivered the first segment in the beginning of the year. So here you can see a stack of 9 segments in a box before they are shipped by boat through the Panama Canal to Chile. They received, so you see this was packed end of 2023, sent early 2024, received a few weeks later in Chile, in Paranal, and the first segment has been coated very recently. And so this is the first step for the ELT. So, conclusion. So this is where we are. So you see we are filling the M1 bit by bit. We have actually started more than 300 segments today. We have currently 190 either in production or packed, waiting for being sent, and we have already sent 126 segments. We are making them at 700 segments per week. And well, if you're there, it's either because you will use these mirrors for your research or you are interested. So if you have some interest, if you want to make some internship, if you're interested in working with us, don't hesitate to write me an email. Thank you. And if you have any questions, they are welcome.
Exactly. So do you have any questions?
How can one work remotely with you? Is it possible that, because I'm not from Europe, so if I want to work with you as an outreach professional, not as an engineer, is there any vacancy?
As an outreach professional, I'm not sure. To be honest, we are a big company, and we already have a lot of people in-house. So I'm not sure.
And does ESO or SAFRAN group does educational resources?
So SAFRAN, probably a bit, but you know, SAFRAN is mostly focused on aircraft engines. So I would be surprised if they do outreach on mirror manufacturing. We are only a small subsidiary of the company. ESO, they are definitely doing some. You can contact them. They have ESO being a trans-government entity, they may be more interested in outreach than SAFRAN. Welcome.
Any other question? Yes.
How much weighs and how much costs one segment?
So how much weight is about 250 kilos typically? And the cost, so this is actually difficult because there are a lot of equipment that we are not manufacturing. The rough estimate I could give you is between 200 and 300,000 euros per segment.
You talked about some aspheric lenses or profiles. Why do you use aspheric profiles instead of spheric ones, and what are the shapes?
So this is a very good question. Typically in optics, aspheric profiles are used to ensure the best image quality. So actually you have to use aspheric profile both for the segments and for the optics made for testing the segment to ensure that you have good enough optical quality. Otherwise, typically you have to imagine the typical problem is if you have two stars very close to each other. So the resolving power is how close can they be, so you can see two and not one. And so you have many things that limit resolving power of an optics. So you have the atmosphere limits it, you have the polishing quality, but you have also, let's say, what we call the optical prescription, so the shape of the optics. And aspherics are let's say, the first step in having a better resolving power.
Is there any questions?
This is a really good picture of your progress, but is there a reason that for the order of manufacture? Like I see the mirrors on the outskirts, which are the same type because they have the same position. Why? Like, what's your?
Yeah, I can maybe answer. So actually, you see this black part. It's been it's put option in here because it's only been recently ordered. Typically, segments are more spherical in the center than on the edge. You have to think that's a parabola. So in the center, a parabola is like a sphere. On the edge, it's flatter on the radial side. So actually, these ones are the hardest one to make on the ALT. These are the most aspheric. And when we have made the contract, so we did the easiest one first that were ordered and then going outwards. But the client, ESO, wanted to check that we are able to make the most aspheric one in the beginning. So actually we did one here, one here, one here to check the manufacturing capabilities. And then we went back here and going this way.
Perfect. Any other questions?
No. So Well, thank you for this really interesting presentation, which was like maybe a bit different than the previous one we had in this congress, but was, I believe, really complementary. And in the next editions, I believe we will have to integrate like more engineering presentation, because they are, I would say, research is made by at the same time theorists, but also experimentals, and so this is extremely important. Thank you a lot. So. So, we are now reaching the end of this first edition of the International Congress of the Astronomical Youth. This had been approximately a year of work for both of us and for the team. We will thank them, of course. This is, I believe, a pretty impressive success for a first edition. And when we started this journey a year ago, this last summer, we had almost no contacts, no organization. We had almost nothing, and we successfully made this up. And even if we are not extremely numerous in this room today, we had during the previous days and this year, we had made a really numerous amount of bonds and connections and partnerships that will be extremely useful for the future years. This year's edition was a bit special because it was the first one. And when you are doing the first edition of something, even if you have like all the greatest partners such as the International Musical Union, when you are not known, it is really hard to gather people and to like present your project. Because when you are coming to ask for funds or anything else, and you are coming like, hey, I have this project, but you cannot show any pictures of what you already did. You have no, proofs of your capabilities. And so this was maybe one of the hardest parts to reach out. But now that we have this first edition, that is, I believe, a clear success, we can move on. And for the next years, we can go back to some partners that we have contacted this year and that were like, okay, this is great, but we have to see something first. We have to be sure that we are able to lead this. And now I think that it is pretty clear that the ICAY is something concrete. And now for the next years, we are able to move on those topics. And furthermore, there's all of this sort of institutional dimension. But also there's the human part. And a lot of people would have loved to come to this edition, but we're not able to do it due to visas or the short delays that we have been given. And next year's, we'll have a better communication on this. We have a better network to communicate, to make the reservations. We have now links with embassies and the French diplomacies. And so all of this will, give us the capacities to make a lot more people to come and to reach out to many more universities. For example, the American Astronomical Society is already planning to send a delegation for next year's. And also, this was a real pleasure for me to see all of you. For example, there's in this room some people we are knowing for a long time, like Nicholas. We are knowing it since a bit more than a year. Gabriel Delerin too, the president of the Astronomist Kingdom. And also now we have all those sort of contacts. And in the next years, as was Jean-Philippe Izan saying, next year it will be still hosted in France because due to logistical and technical reasons, it will be really, easier to tighten the loose ends. But the year after, so in 26, we are really thinking of exporting it to another country. And due to the real connection, we are now really seeing the people. We have real bonds. And I think it is really possible that we are, moving on another country in 2 years. So, and I feel this is only the beginning of an impressive journey. And I think that when you started this 1 year ago, it was the main idea was just like to have a sort of, how to say, just a meeting. We were like just two students entering university, and we were like, okay, we're just going to gather some people and to do some astrophysics together, and it would be something fun. But with, I would say, increased importance and the, how to say, the really fast-growing, actually, curves of the ICAY, when of course, this is still like the main purpose doing science. But now we have another mission, a really important mission, which is sort of, how to say, not given to us, but really supported by the International Astronomical Union alongside other organizations, which is to gather astronomical society throughout the world, because many countries have a physical, how to say, not physics of course, but astronomical societies. Sweden, French, Africa, everything, Morocco, all of them have some, but there is till today, there's almost no links between them. There's no comments and shared events. There's none of this. And this is like a real deficit, I believe, in the scientific world today, because, okay, I know astronomical societies are mostly made of amateurs and students. There's, of course, some researchers in them, but not that many. And but what we have to understand is that in this society, this is like sort of the future, as was Deborah saying, because students are, of course, and some people in this room are like the future, the next generation, the upcoming generation in cosmology, in astrophysics, in paleontology, and we have to really develop this kind of network, because as was Jean-Philippe Usan saying also, is that in research, to do good work, to have access to good data, it's really like a mattering thing to have many friends in other countries and other organizations. And so we are hoping to build an international circle that will, I would say, gather all of these institutions, students, researchers, countries, embassies, to like really, how to say, give the world community of research in astronomy and physics a new breath and a new way of
mostly
careers.
Being a facilitator for the astronomical projects and cooperation around the world. So, as Melon said, this is a crazy project for two students nearly starting in this field, and we were supported by lots of people and institutions, such as, of course, the International Astronomical Union, that we really want to thank for the support and just believing in that just crazy project, because there was nothing at the very beginning. And even the very concept of this Congress is to gather and just to fit to the very concept of science, that is to share same passion and just having fun with that, and just sharing experience, knowledge, talks, etc. And that is what all of our other supports have understood and was following us in, as the ICAY, the French International Radio, the BIPM, International Bureau of Weights and Pounds, etc. Of course, we really wanted to thank also the French embassy to Pakistan, that supported and created a great grants for our representative from Pakistan, and those all supports at the French Astronomical Society and L'Astronomie magazine were very just needed and obligatory to this event to be. So really thank to them, and I think we can applaud them because I'm sure they will see that. And when we are doing that, we also wanted to really thank all the team that were supporting and really worked a lot in this project. We were like 20 people working on the D-days of this weekend, and more than 30 people all through the year of preparation and work. it's more than 30 people and a lot of hours. We are just with two of us, we are just at 2,000 hours. If we add all the work, we are nearly at 5,000 hours of work of all the team in that project. So I really thank everyone in the team. So really thank you, and I think we can applaud them even more.
I just add that another impressive thing is that many of the team members are been meeting the first time, in fact, Thursday morning, because all of this had been planned online, and so the very first day of this Congress, it was also the very first day we met, and so I would say achieving such a sort of symbiosis for the live diffusion and everything was really impressive to them.
As you even more, because it's 5,000 hours this year with the whole team. We were 20. Imagine what we can do if we are like, I don't know, 50, sorry, or even more. We can just multiply the size of this Congress and the impact it has on the astronomical societies around the world, on the just astronomical community, etc. We can really have a power as the astronomical youth, because we are less heard than other community, even in sciences. So I really think that gathering everyone and making us a union can really be a good project to just have our voice. Adapt to make everyone welcome in this team. So we are even contactable just right now or by email, etc. And I really thank you everyone for this year and next year. So we will see, I hope everyone, you are all invited in the ICAY 25 that is now officially announced. And so really thank you everyone and see you next year. À l'année prochaine.
Merci.